Okay, well, welcome everybody to the SZ4D Town Hall for today. We really appreciate everyone taking some time out of their busy schedules. It feels like it just gets busier all the time for us in this working from home mode that we're still mostly all in. We are going to have a 2-hour program to really kind of update people on a lot of the very active work that's been going on through the SZ4D working groups and integrative groups. We have some new things to introduce today, actually quite a lot. So without much ado, I will jump into it. If I can make the slides advance, that is. There we go. Okay, so first I want to first of all, my name is Harold Tobin. I'm a professor at University of Washington, Seattle, and I chair the steering committee for the SZ4D group, but that group, as you're going to see, represents many dozens of people who are working actively, plus really the many hundreds of people who have signed up and engaged with us in input through all of the different interest groups for SZ4D and all the communications that we have. We're going to spend a little time today really giving you a very brief overview presentation. I am guessing that the vast majority of people who have joined us today are already at least somewhat familiar with SZ4D, but not necessarily. So we'll do some basic introduction to the initiative. And then we're going to spend the bulk of the time in the first hour with direct updates from these 5 different groups that are actively engaged in planning the SZ4D program. A new one, building equity and capacity, that we will talk a bit about, and then direct updates on very active working group developments that are happening in the various sort of scientific thematic working groups, and the model and collaboratory for subduction. We're going to then switch over to an opportunity for everyone to have input to SZ4D and to what you have just sort of taken in from, will have just taken in from the presentations by the different groups, and a chance for feedback. So we'll explain how the breakout groups are going to work, and we'll go into breakout groups kind of towards the end of the first hour here. We'll have, hopefully, I'm sure it'll feel very quick, but a good amount of time for some great breakout group discussions. And then we'll come back and really kind of summarize what was actually discussed in the individual breakout groups, and use that as feedback to all of the groups that are working hard on SZ4D implementation plans that are coming up. And we'll wrap that thing up, I think, by the end of 2 hours. You'll hear from a lot of different presenters over the next hour or so, and probably take in a lot of information. And hopefully parts of it will be very new, and parts of it will be familiar to you perhaps from what you've already heard from our groups, but things are happening fast in SZ4D world right now. A lot of activity is going on in terms of planning for the potential, we hope, in implementation of an SZ4D program as time goes by. All right, so I'm going to spend just the first really few minutes on a kind of a broad overview, and then turn it over to a series of other speakers who are going to talk about the different group activities. So first of all, just to make sure that we're kind of all on the same page, maybe you're new to this initiative or have heard the buzzword, maybe even taken a glance at our website, but really don't know what's going on with this program, because it is very much an initiative that has been in development for a number of years, but is in the planning stages now, and we hope will become a very major part of our research community in subduction zone science for years to come. So SZ4D itself, subduction zones in 4 dimensions, or maybe subduction zones through time and space, is a research coordination network, which is an NSF term actually for a structure that NSF uses when big new initiatives are starting to kind of come together and develop in the scientific community, usually through grassroots kind of growth, as this one has very much done, and then use that as a vehicle for a planning process. So we were funded actually as a 3-year research coordination network, and the focus is on fundamental science, fundamental geoscience that underlies hazards, including things like earthquakes, tsunamis, volcanoes, and landslides, and specifically, of course, at subduction zones. It's funded by a broad consortium, or a broad range of NSF programs, 5 different programs in OCE and EAR at NSF in the US. And the activities were explicitly designed to fund this planning process, to develop working groups that you're going to hear from, integrative groups, run workshops and webinars and town halls like we're doing today, and ultimately have that culminate in an implementation plan or a blueprint of sorts for what an SZ4D program might look like. The goal is a comprehensive observational and science plan to improve our understanding of these catastrophic geohazards. It's based very much in this document, which if you haven't looked at before, you certainly should, the SZ4D initiative, what we call the vision document, published a few years ago now. SZ4D was also highlighted very strongly by the National Academy's recent decadal report, Earth in Time, or the so-called CORES committee report. That is NSF's sort of guiding document for the next 10 years of priorities in the earth sciences. And it came out of course, a range of these workshops that happened a number of years ago and really fed the ideas that went into the vision document. So if you haven't looked at our website, of course, look at it more. Sorry about that, went the wrong direction. You know, in a word, why subduction zones for a geohazard focus, since geohazards are ubiquitous? Well, you know, I think that everybody probably who's bothered to join a meeting like this could agree or understands that the world's largest hazards really are all present in many ways and converge in subduction zone setting. Tectonic forcing of geohazard is turned up to 11, so to speak, at the subduction zone locations in ways that integrate a number of different things all into one sort of geographic space on the planet. And scientifically, subduction zones, you know, provide natural laboratory conditions that are conducive to really making advances in doing the science underlying these systems. Controlled conditions that have systematic variables, so a long strike variation, for example, in subduction systems, is one way to really isolate conditions and look at variability in all of these systems. So SZ4D was structured initially to basically dive down deep into those three kinds of fundamental sets of geophysical, geological, geochemical conditions that generate hazards, tsunamis and earthquakes, eruptions and landslides, and look at that science underpinning those by developing these working groups that you're going to hear from in substantial amount in just a few minutes. Faulting and earthquake cycles working group that's focused primarily on the earthquake problem, magmatic drivers of eruption, and then the landscapes and seascapes working group focused on the surface processes that link the volcanic systems to, let's say, arc to trench, to use a shorthand version of it, and the combination of forcings and then transport of material that drives surface process geohazards. So that's the sort of underpinning structure of having these three working groups that are on these three scientific themes, and we're working hard at the moment to stitch those all together and really develop a science plan that is a unified subduction zone whole. So the RCN process has 3 years plan, and we're actually about 2/3 of the way through that now. And as you'll see, we're aiming towards developing an implementation plan to be completed and essentially published or put out there and put to our potential funding agencies for an SZ4D initiative by fall of this year. It has a structure that includes those three working groups in shorthand that I just discussed and a steering committee, but also two integrative groups that are focused around designing inclusive plans for, you'll see that the title is different from this, not education and outreach, but building capacity and building inclusive site structures in our groups, and the modeling collaboratory, which is really about modeling the systems and processes that are relevant to all of these groups. So that's why we're calling them integrative groups across the way here. And there's another one that we're not going to talk about too much today called Converse, which is about rapid response to and understanding eruptive processes that came out of a very strongly allied and parallel structure, and is another NSF RCN, somewhat separate from but highly linked to SZ4D. So we're working to work with the partners and funders to bring all of this to fruition by designing a program and a process. So the implementation objectives include designing and creating a potential or advocating for physical infrastructure, direct measurements, observational systems, including large-scale facilities and long-term rapid response capabilities, and the cyber infrastructure and data management to handle all of that, to capture processes in time, which is the essence of that SZ4D concept, using time series understanding and all of the modern tools of observation, and that time spanning not only observational time, but also geological time and things that happen through the laboratory and other stuff. We'll hear more about that as well. And then in parallel to that, also building an intellectual infrastructure, meaning a science program that uses, takes those observations and leverages them, uses models and experiments, and has a scientific community that's putting things together cohesively, is inclusive, is engaged, and is internationally engaged and develops capacity across the globe. Although this is initially a US-built science plan, it is intended very strongly as a subduction zone international community in the long run. And so all of that goes into building that intellectual infrastructure to capitalize on the physical infrastructure. Okay, we're going to hear from all of the working groups, and they have, been working extremely hard over the span of the past year and a half. The first actual meeting in person of the working groups was a little more than a year ago now in Albuquerque, New Mexico. This year has, of course, thrown us some loops in terms of how to work together, but the working groups have been doing an incredible job and meeting constantly to develop, ways that make sense to address these questions. I'll talk about them in a minute. I won't talk about the questions now because you're going to hear from each of those working groups in just a second. But each of the groups, one thing that's happening in common from all the working groups is that they are taking this deliberative and structured process to do that, grassroots work, meaning take the input of the scientific community very broadly, develop sets of hypotheses that make the most sense and have the highest priorities for those working groups for things that we can really tackle and address in an SZ4D program. Take sets of observational information, databases and inventories of whether that's volcanoes, whether that's segments of megathrust offshore regions and everything in between, and run something called a traceability matrix, a very sort of specific process to kind of take how can direct observations that we have and can make and or models, et cetera, directly address the hypotheses and questions. So the process has been, tracing those goals to specific program elements. And I think you'll see in the presentations to come that that's exactly what's been happening in this planning process. The inventories are started out from looking at subduction zones globally and really looking at the characteristics of all of them and building these kinds of inventories. And members of the working groups have been hard at work with all of this. Those processes, those analyses are in process now. You'll hear that there is, as the hypotheses and questions have been honed and winnowed down, geography is the next big step in determining where these things might most fruitfully take place in a potential program. You won't hear answers to specific places where SZ4D is going to definitely go today, so much as an understanding of that process of how to choose those things wisely and in ways that would make really the best sense to get the most bang for our buck, so to speak. Okay, so the working and integrative groups have been doing a tremendous job. I mean, I can't believe how much work we've asked people to put in, and they've stepped up. And there are quite a few people. There are more than 70 members of all of these groups, from the modeling collaboratory through the working groups to the new equity and capacity building group, meeting very often and doing the hard work. Those groups have just produced draft versions of some of the answers to those questions that were in the previous slides, and you'll hear about what they are working on and how they've put that together so far. And we're doing the work now to stitch all of this into a sort of the broader statements about what the implementation looks like. We have the interest groups that many of you are members of, and the mailing list. There are probably well over 800 now. This is changing every day in terms of people that we're reaching out to and trying to get communication back and forth from. As part of that process, we've run town halls and webinars like this quite frequently this year. We're also doing this series called the International Webinar Series, where we're trying to hear from our international science partners who are the experts on all kinds of parts of the subduction process, but not based in the USA. And we've had a number of them. You can see video recordings of all of those previous international webinars on the website. And the turnout's been phenomenal. We've been very happy with the number of people who've engaged. I think this has been a huge immediate benefit of building an SZ4D community. Okay, so the timeline for where we are headed and what's going on right now in 2021, we will address this a little more right at the end of the town hall today, but just to give you a flavor for where we're at, the working groups have been drafting these detailed science plans and objectives, just completed first drafts. These are internal right now, but you're going to hear the summaries of all of those today, and we're building that up. The building equity and capacity in geosciences and the modeling collaboratory integrative groups have been meeting. This one in particular has just started its operations. We'll hear some exciting things that they're doing. The MCS volcano workshops are in progress right now, going on all the time. We a huge amount of in-depth work on modeling collaboratory for volcano processes is taking place in there. The SZ4D team, with some specific PIs headed up by Diana Roman from Carnegie Institute, submitted an MSRI, or mid-scale research infrastructure proposal to NSF. NSF encouraged us to use this as a vehicle for starting infrastructure plans. It would be for a design proposal. It's a pre-proposal currently pending, so we don't know what the answer to that will be, but that may go to a full proposal, which would be due in April. We're going to follow this up with additional town halls. The implementation drafts based on these chunks that have just been drafted we plan to have come together by early in the summer. June 1st is our target, and we will have an open comment period for members of the broadest community we can. But we're always interested in input from everyone, and those 70+ members of the working group are all people you probably know or can easily reach out to. So the comments are open anytime, but this will be written comments on this full first draft. And our target is in August for implementation plan completion. The dates are probably less set in stone as we go further out on this process, but we would like to be releasing in the fall a full release of an implementation plan. And we would love to have another very broad workshop for SZ4D, in-person workshop if we can, and that just kind of depends on how the world evolves right now in the pandemic. But that is plausible, at least in the future, and I think our NSF program managers would love to see us do that, and we would love to do that as well. So beyond that is where the biggest question lies. We want an SZ4D program to exist. We would like to see it be a program with not only NSF, but also partnerships with NASA, with the US Geological Survey. There's a number of USGS people who are participants in the planning groups now, and so on. So that's kind of where we stand. At this point, yeah, I will have to exit out and stop the share. And we will go back to the agenda for today. And so that was a presentation. We're going to hold questions because we have the breakout time. So we're going to jump straight to the working group presentations now. And the first of those will be from the Building Equity and Capacity Integrative Group. Mike Brodzinski is going to present. And Mike, you can go ahead and do a share.
Can you see it over there, Harold?
Yes, looking good.
Okay. All right, great. So yes, as Harold has noted, we are a new group that's contributing to SZ4D. Our name is fairly recent, so you'll hear it referred to in a variety of ways. But you know, again, the original charge here was to try and identify the correct set of activities that are strategically useful and maximize those specific assets of SZ4D. So things like geohazards, the fact that it's international, heavy amount of instrumentation, that it's multi-institutional. But I think as a group formed, you know, with a general idea about sort of education and outreach, we decided that what our goal was perhaps a little bit different in the essence that we really were seeking to transform mindset in our community to try and better embrace education outreach, but also capacity building, diversity, equity, inclusion, and social justice, to see those as critically important for the success of the scientific endeavors. That, you can see our name change trying to reflect that aspect of what we sort of consider dear in our group. And that the mindset that came out pretty clearly is that we wanted to think about this differently to get different results, to try and be different than some of our bigger programs in our community. But again, that point about sort of influencing the scientific endeavor, of course, this can be summarized by a well-known science philosopher, MC Hammer, who recently quoted on Twitter, said, when you measure, include the measurer. Present from MC Hammer about what we're trying to accomplish when we consider this aspect of SZ4D. So I alluded to that, there are a variety of things that our group is sort of interested in. So I'm going to walk through a couple of research questions, aspects that our group is considering. We are at less than a month old, so we do not have a sort of well-defined set of research questions that we're focused on at this point. But in our initial discussions, these are ones that sort of rose to the top. And so we wanted to share those with the community to sort of illustrate the kinds of things that we're targeting with this group. So things like, how can we leverage international scientific efforts into the capacity building partnerships that improve scientific capabilities, so skills, data, software, technology, things like that, but to do so for all parties, right? That this is a true partnership that avoids more imperialist or colonial attitudes to bestowing knowledge to folks in other communities. So this was a key component of it, but also thinking about ways that this could be done, that the improvements could be made in a way that is sustainable, not just a parachute in, but to build partnerships that are long lasting and have impact well beyond the sort of time frame this program might even exist. I think there's been a lot of discussion in our group about equity and social justice. We see that geohazards disproportionately affect specific communities, many of those being disadvantaged to start with. So, for us, the question is, how can improved understanding of subduction zone geohazards be used to inform and address social justice and equity issues in hazard mitigation, right? So thinking about ways that the science can help enable improvement in terms of equity for hazard mitigation. I think we're all, of course, also very interested in education, but I think we want to sort of combine that with assessment and inclusion, right? That educational efforts that are more inclusive and have measurable student learning outcomes are needed to equip and diversify our scientific community. So how do we identify, develop, and implement those strategies, right? So identifying is a key aspect, and so assessment is going to be a key component of this. I think also in terms of education, often bundled with outreach, we think that certainly that is combined also now with science communication as a key player in this, right? So a question around this would be, can we establish a more distributed model of outreach by better training members of the SZ4D community to accomplish effective scientific communication and help the general public better understand geohazards and the risks associated with them, right? And so I've shown a example pager diagram here to the right, just to show the sort of two sides to this, right? Pager is a fantastic product produced by our community to sort of try and convey information rapidly about hazards associated with an earthquake. But also it's very difficult for a general audience to understand how pagers are made, what's in it, how to respond to it. So again, there are opportunities, I think, by better sort of developing our people within our community to be able to do the science communication as opposed to establishing just an outreach office that would do that for our community. I think certainly you'll hear throughout the discussion from the working groups the importance of interdisciplinary collaboration. So I think our group is thinking about helping to identify what are the best practices for interdisciplinary collaboration. They break down those silos and improve the understanding across disciplines, right? So in many ways, are there lessons that we can learn from other fields that would inform a more evidence-based approach to what we do here in the geosciences, right? Are there some lessons that can be learned that will improve our ability to do that interdisciplinary collaboration? We can already identify that as going to be critical for the success of SZ4D. So are there some ways that we can use social science literature and other studies that have been done to try and help us accomplish that more effectively. All right, so that's a brief summary of the kinds of things that we're interested in. I want to make sure to acknowledge the team that has formed for this building equity and capacity with Geoscience Group. So that's myself, Jackie, Beth, Michelle, Andrew, and Marie, Christy, Aaron, and Lisa. I wanted to make sure to note each of those people because we have some folks that are embedded in the working groups, but then we have some folks that are external to SZ4D and some that are outside of geoscience entirely. So again, we're trying to embrace that sort of nature of thinking about this in new and different ways. But this is very early in the progress bar. So please reach out to us if you have any feedback, any way that you'd like to participate in our group. We'd love to hear it. Thanks.
All right, thank you so much, Mike. That's great. I'm looking forward to seeing that progress bar. Keep moving along. The next one up is Magmatic Drivers of Eruption Working Group.
Okay, can everyone see my screen there?
Yes.
Looks great. Thanks, Pete. So I think I'm going to kick this off. Hello, I'm Terry Plank from the Lamont Doherty Earth Observatory and Columbia University. And together with Peter LaFemina from Penn State, we are representing the Magmatic Drivers of Eruption Working Group. You can move to the next slide, Pete. And so this working group consists of 17 very hardworking members on behalf of the community, to define the MDE goals and implementation. We also represent over 150 interest group members. Please join if you haven't already, and please reach out to one of us if you have any input or comments. Next slide. So our central question, which we spent some time developing, is how do transcrustal processes initiate eruptions at arc volcanoes? Each of these words has meaning. So transcrustal, meaning the arc volcano is the top of a transcrustal magmatic system that actually extends into the mantle and connects to the subduction zone. And that initiation is, we can all agree, the initiation of eruption is a critical event that moves the system from quiescence to unrest. And obviously the importance of the arc volcano. They form over subduction zones and are also the major current volcanic hazard to the world's populations. So in a way, this picture does contrast a bit from geoprisms, which I say had maybe a bottom-up perspective, connecting the slab and mantle wedge to the surface. Here in SZ4D, it's a new focus really on the eruption on volcanoes because there's been a lot of excitement about the advances in volcano science, the promise in volcanic forecasting, and all that can be gained from new academic and observatory partnerships. But as this hokey diagram suggests at the bottom, there hasn't really been a great integration of the transcrustal volcanic system to the mantle, that many of the volcanic pictures stop at the MOHO. And SZ4D is really about providing a new opportunity to connect the volcano to the magmatic production in the mantle and subduction zone. So next, I want to show you a little bit about how we've moved from this driving question to what will be notional experiments. So this is an overview of our process so far. Harold showed a preview of this earlier. If you've been involved in previous town halls or you've been part of our interest group, you know that we've been developing with community input this hypothesis grid that connects eruption drivers, say supply rate of magma and volatiles, those are the ultimate drivers, the depth and distribution of magma, and rheology and stress state. We'd say these are what are driving the system to the run up to eruption, to the repose of eruptions, or even failure of eruption and creation of plutons, to the style of eruption. So that's what makes the grid of our hypothesis grid. And then we developed a traceability matrix to match what will ultimately be our field and lab experiments to these scientific objectives. We actually had the community vote. So many of you voted on our hypotheses and which you found most compelling. And what actually emerged was a trio of hypotheses with input from the community on other hypotheses in this grid. And that this trio is really what will drive the notional experiments. So next slide, I'll go through these three, our trio. So the first is about how mantle magma supply rate links to eruption intrusion and their likelihood in the evolution of the crustal magmatic architecture. So yes, magma supply rate is the focus here. In a way, it's the holy grail. It's something we actually don't have great constraints on, but we know it sets in motion much of what follows. The residence time of magma, the storage depth, its evolution, its staging. But it's something we just don't have great constraints on. And to me, this is the whole purpose of a big initiative like SZ4D, is to focus on the tough problems like how subduction leads to different magma supply rates that then create this cascading effect through the transcrustal system. So the critical scientific needs that we've identified to address this hypothesis involve high resolution imaging, detailed mapping, and then importantly, for these high resolution and detailed mapping efforts, this would be a small number of volcanic systems. And therefore, our hypotheses are leading to how we're planning to approach them. And Pete's going to fill in more on where those approaches are going. But let me go next to the second of our trio. And this has to do with how gas and magma chemistry link to eruption run-up and intensity. And this is really motivated, like this image shows, of the new time series data that have come out in one example of gas composition, which turns out to be a new precursor to eruptive activity that we didn't know about. These hypotheses relate also to how mafic input is important in rapid run-up and eruption frequency, and then how we connect the gas and the magma input and how they interact to control eruption intensity. So here the critical scientific needs then are constraints on magma supply, on these time series of gas, chemistry, and outgassing. And importantly, this approach involves study at a large number of volcanoes. So you can see already that the implementation plans we're recommending have different scales. Okay, so the third trio here has to do with external triggers of eruption occurring over different periods. So glacial unloading, for example, might trigger eruptions over tens of thousands of year time scale. Sector collapse, which can happen either hydrothermally or through dome growth, might happen over years or months. And then static and dynamic stress triggering, say from local seismicity, could happen, or faraway seismicity could happen over hours and seconds. And so this then determines the critical scientific needs over different timescales of geophysical observations, gas chemistry again, over the shortest and medium timescales, and then indeed landscape scale and geological and geochronological studies over the longest timescales. So importantly, these external triggers of eruption integrate the potential to integrate with earthquake and faulting and the landscape and seascape working groups. So from here, I'm going to turn this over to Pete to now turn these into the kinds of experiments that we envision doing.
Hi, Terry, thank you. So to address our scientific goals and address those hypotheses, we've come up with several notional experiments and instrument deployments. But before that, there's an immediate set of science activities that we can do to precede those experiments. So what do we want to do? Well, we can use existing samples. We all have samples lying around, and petrologic studies of those samples, as well as laboratory experiments, geophysical studies, and even physical models. And that would allow us to address some key things before we start our notional experiments. And those include being able to constrain the architecture, composition, thermodynamic state of both current and active and extinct magmatic systems. We can look at lab experiments and development of new methods, for example, developing new diffusion chronometers and barometers. And we could tie these all together, including the geophysical and petrological constraints, and create cohesive models of our magmatic systems, from looking at magma flux through the conduits, magma flux from the mantle, including subduction zone dynamics, and real rheologies to all these systems. And what's great about this is it allows for immediate and direct ties with the earthquakes and faulting group, the landscapes group, and the new building equity group, as well as our MCS, the modeling collaboratory RCN. So our first set of notional experiments, as Terry alluded to, is to look at many volcanic systems, but sparsely. So we're talking 30 to 50 active volcanic systems distributed globally. And so that would allow us to instrument a large number of volcanoes with a whole suite of multi-parametric monitoring equipment, gas, seismic, acoustic, deformation, you name it. In addition, bring in the latest in remote sensing capabilities. I think many of us are looking forward to the NASA NISAR mission for looking at radar data globally, as well as the existing data sets. But there's also a whole suite of other remote sensing observations that we could tie to this. And the goal here is to observe the run-up and syneruptive processes that are occurring at these many volcanic systems. And so, for example, here's an active volcanic system, and looking at things like the flux of CO2, SO2, hydrogen sulfide coming out of a volcanic system over time, and what do those signals look like, or the seismic events or number of seismic events, the type of seismic events that are coming leading up to an eruption or during an eruption or even following an eruption. Now, following an eruption, we want to be able to look at the eruptive products for petrological evidence, for example, of mafic rejuvenation, and be able to conduct experiments on those to, again, tie what we see in the petrologic record to those geophysical signals. So this is our suite of many sparse experiments. The second type of notional experiments is few, but very densely instrumented experiments. And so here, our goal is to quantify, again, magma supply rate, depth and geometry of the magmatic systems, but at a few strategically located systems. In addition, we're going to want to bring all of the instrumentation and goals and hypotheses from the many experiments to dwell on this. So some of the things that we're going to want to do here in detail is look at seismic tomography, magnetotellurics, ambient noise tomography, things that allow us to image this transcrustal magmatic systems and ultimately image the flux of magma from the mantle to our volcanic systems. So we'll also want to look at gas fluxes, geodetic imaging and monitoring. Again, bringing in remote sensing observations to do this. And then also look at, again, look at that petrologic evidence for these processes. The last part of our notional experiments is to actually look at the exhumed systems and past eruptive records. And so this allows us to look at, really go back in time and see how these systems have developed. So what we want to do is look at inactive systems that have been accreted and exposed, arc plutonic rocks or volcanic systems, and past eruptive records. So we're going to want to use geochronology, barometry, and again, petrologic studies to investigate how these systems have evolved over time. And finally, to actually determine where we're going to do these notional experiments, we've come up with certain site attributes that we think are important to be able to address our scientific goals and hypotheses. And so here's a list of what we've been interested in looking at: active systems, systems that we know the frequency of eruption, systems that are logistically feasible to go to, a good fit with the other interest groups, so we can have synergies there in terms of instrumentation, previous characterization of those systems, a diversity in volcanism at one subduction zone if possible, and a diversity in subduction parameters. So some of the things that, some of the places that we've come up with are shown on this map here, but South America, Central America, Alaska, Japan, and regions that have exhumed paleo-arc are what we're looking at. And with that, I will pass it off to our next group.
Great, thanks so much to both of you. Without any waste of time, let's move right on to the faulting and earthquake cycles group.
Hi, everyone. Thanks very much. Can you see my screen okay?
Looks good.
Hi, everyone. My name is Donna Shillington. I'm from Northern Arizona University, and myself and Emily Brodsky from UC Santa Cruz will be giving you an update on the Faulting and Earthquake Cycles Working Group. And this presentation will be given on behalf of all the fabulous members of our group who've all been working very hard. So hopefully we'll do justice to them and to the feedback that we've gotten from the community. So the real motivation for this part of SZ4D is understanding when and where do large and damaging subduction zone earthquakes occur. And we've kind of devised 4 questions that sort of cover subparts of that broader umbrella question. So the first is, what controls the speed and mode of slip in space and time? Over the last years, we've seen all these different ways that subduction fault zones can behave. And by studying and understanding the spatial and temporal relationships between areas of geodetic coupling, where large earthquakes occur, where slow slip and other kinds of slip behavior occur, can give us a new window into controls on subduction zone deformation that we didn't have before. Our second question is, what does distinctive precursory slip or distinctive foreshocks exist before earthquakes, and what causes it? There have been a number of exciting studies, such as the one here on the right, that have documented behavior before large earthquakes, such as migrating precursory foreshocks. But when we look around globally, the existence and style of precursory behavior vary a lot. So we still have a lot of questions for identifying precursory behavior as such and understanding what causes it. Our third question concerns what controls the tsunamigenic potential of subduction zones. Again, there are a number of controls have been proposed of why some places make larger tsunamis than others. And so another goal of our program is tackling that. And finally, we know that the main plate boundary fault is not the only important fault in the system for accommodating deformation and for accounting for hazards. We have this whole network of faults in the overriding and downgoing plate that are accommodating deformation, enabling exchanges of fluids, and so a kind of holistic understanding of deformation and hazards in the subduction zone needs to include some of these other fault systems as well. So armed with those, our umbrella question and those 4 questions, the work of our working group has been, as the others, to develop a strategy to try and tackle those questions. And so this includes both figuring out what we need to do to tackle the questions, what kinds of observations, models, and experiments are required. And to that end, we've developed a traceability matrix, which I'll show you a little bit about to link our questions to the specific activities that are necessary to address those questions. And from that, developed plans for notional experiments that and activities that we can undertake to carry that out. Of course, another big question is, where do we go to tackle these questions? And for that, as described just for the Magma Drivers Group, we've kind of outlined a set of attributes that we think are important for subduction zones to possess in order for us to tackle our questions, and a subduction zone inventory. And so by combining those can provide a science-based and rational framework for trying to make future decisions about that. And of course, the who is you, hopefully in this town hall, and going forward, we really need your feedback and engagement in order to make the strongest plan that we can. So now I'm gonna start off with the what here, and the traceability matrix. So the kind of the goal of this activity was, again, to outline for each science question, what information do we need to know to tackle that question? What specific information do we need? And what kinds of activities or observations can actually provide that information? And so here's an example of a traceability matrix for one of our questions. And the color coding is by discipline. So yeah, there's nothing as exciting as walking through the details of a colored in spreadsheet, so I won't do that, but I just want to give you a feeling for kind of what's in here. And there's kind of 2 categories of activities that we've identified that we think are important. And the first is actually obtaining new constraints on how subduction zones are behaving. And the first part of this involves observations of present day behavior over temporal and spatial scales, and at sufficient resolution that we can actually capture meaningful scale of process and the full diversity of behavior of what subduction zones are doing. And observing those behaviors offshore is a particular gap currently. But the other piece of this is that we need a deeper time understanding of the history of earthquakes and of kind of geologic timescales of process. And for that, we need paleoseismology and geology to provide. And so if we go back to our very exciting spreadsheet, we can see that kind of documented through here, that for the kind of modern geodetic coupling and slip behavior, we need combinations of amphibious, geodetic, and seismic observations. But to provide the larger scale picture requires paleoseismology, numerical modeling of those kinds of constraints, and legacy seismic data to help fill in the deeper time part. And then the kind of second category of things that we think that we need for all of our questions are kind of geology and physics to actually understand why subduction zones are behaving how they are. And that's this second part. And so this involves characterizing subduction zone configuration and properties at a huge range of scales, from the detailed geologic scale of materials and their properties along the plate boundary to the broader scale configuration of the subduction zone. And for this component, we feel that we need highly integrated and diverse observations from geology and geophysical imaging and experiments and numerical models to help tie all of those things together. And so the kind of second part of our traceability matrix here is detailing those. So for the particular question I'm showing you, many things have been proposed to control the mode of slip in space and time, including from the large scale configuration to heterogeneity at various scales, the distribution and pore fluid pressures, and other things. And so you can sort of see this suite of geophysical imaging, geology, experimental, and numerical efforts that would be required to fill in all those pieces. And so we've recently distributed this traceability matrix to our interest group, and we can do that, of course, here again today. But what we critically would like to know is, have we missed anything essential in here in terms of critical activities that we need to make progress on each of our questions? And kind of from this traceability matrix, as exciting as a matrix is, it is like driving a lot of what we're doing. So we really need your input. And so this has informed the development of our notional experiments, and I'll turn it over to Emily to describe those to you.
Okay, I'm Emily Brodsky from University of California, Santa Cruz, and Donna got to do the matrix. I get to do the cartoons, which is that what we're going to do can also be, you could also ask, how do these activities intertwine to actually combine to an overall strategy? And I think we're pretty clear, and it should be clear from the matrix that Donna just presented to you, that what needs to involve collecting new data. We do need, in fact, more information about the subduction zone interface and its accompanying faults. And we need it on a fairly large spatial scale. What we know about slow slip regions is, and variations of coupling, is that meaningful segments exist on something like a 500-kilometer scale, looking at places around the world like Cascadia, Japan, Hikurangi. That's kind of the scale at which there are meaningful variations in behavior. And so since one of our key strategies that is coming out of those scientific questions is to be able to compare slow slip and locking, to compare behavior, we need to be working on that scale. And so ideal study sites will exhibit variations in slip behavior and allow us to compare and contrast. Next slide, please. And so in order to do that, we need to observe things. And observing can mean instruments on the ground or under the water, especially under the water. That includes geodesy, seismology, and geophysical imaging. And these are kind of scary and ridiculous cartoons with lots and lots and lots of dots on them. But I want to point out that these dots are not arbitrary. Densification is actually scientifically incredibly important. This geodesy cartoon is constructed specifically with dense enough dots near the trench that you can, in fact, image the interface, or learn about behavior on the interface. And the density between station needs to be on order distance depth to the interface. Otherwise, it doesn't scientifically work. And so densification is a huge part of what needs to be done to, in fact, answer the scientific questions. Next slide, please. Data doesn't just mean bits in a machine. Data comes in many forms. And data, one of those forms is geology. And in order to be able to understand an earthquake cycle, given our limited lifespans, we need paleoseismology. We also, in order to understand what is happening on an interface, which is buried under kilometers of rock, we need geology and we need analog sites. And so a plan for those activities needs to be crafted as well. Next slide, please. So all of these need to be interleaved, and we need to try to sequence these activities in a way that we're not going to get to the end and regret that we didn't do that key thing at the beginning. And so in broad brushstrokes, there's phase 0, phase 1, and phase 2. Phase 0 is where we are now, which is preparatory work, which includes analysis and synthesis of existing data. And there's an awful lot of that out there to help guide the future plans. It also includes technological development. The actual instruments we do need and the models we do need don't actually exist yet. And so, for instance, I think Harold very briefly mentioned the MSRI pre-proposal that was put in by this group and what that included is technological developments that need to happen in order to do anything else later on down the line. So it's very important to emphasize that that is a SZ4D proposal, not the SZ4D proposal. And it included technological development actually for all 3 working groups. Also phase 0 includes planning and partnership. Phase 1 is reconnaissance, which is you might have noticed the last cartoons had areas of slow slip and areas of locking. You need to know where those are in order to make the dense instrumentation. So some recon work is required. And so backbone instrumental data, recon is also required geologically, and in all other fields. And then finally, hopefully, we will get to a detailed study where we really get the required densification, which is fully informed by the prior work. Next slide, please. So where is this all happening? Nobody's going to give you an answer to that because nobody knows an answer to that. And nobody's going to give you an answer to that. We all need to come up with an answer to that. What we are working on is a rubric. A deliberative way to make these decisions. And so what we've tried to collect together here are what are the attributes of a subduction segment that would be suitable. And they've been divvied up based on whether they're scientific attributes or other kinds of attributes. And we live in the real world, and obviously practical and logistical considerations come to mind. So the scientific attributes are mapped very specifically to scientific questions, and you can see that they therefore fall into high priority that address multiple questions or are particularly critical to answering the questions that we simply couldn't do those questions without, and then things that would be certainly an advantage. And then what we've been doing with these attributes is to start to try to focus down on the scientific high priority ones and populate those for subduction zones around the world. The idea being that there's no point filling out every single attribute for every single subduction zone when we have some subduction zones that scientifically wouldn't do us any good. So we can use these high priority ones as something of a screening. And then once we've got a small short list on this high priority, then we can start to consider the practical and logistical challenges. We really want feedback in these breakout groups and through the survey afterwards and through emails to whether or not these are the right attributes. What are we missing? Do we have this right? Because this rubric is going to become very important. And so we'd like your feedback on it. And then next slide, please. As I said, these are then the scientific one, high priority. We have a first cut at populating those attributes in this spreadsheet, which is linked on the bottom of this page. Just take a screenshot of it. Obviously, you can't copy it in real time. Just take a quick screenshot. We would like your feedback on whether or not we're working with accurate information. All right, next slide, please. The same activity is going on with the analog sites, and that onshore analogs for subduction zones around the world. We're trying to collect an inventory and so that we can sensibly make sure that there's the geological record exists for what we want to do. And then next slide, please. Feedback, please. I've gone over my allotted times here. I apologize for that, but we're going to do breakout groups in a minute, and we'd like feedback specifically on the science questions. Those science questions did come out of community documents, so I'm hoping that over the years of vetting those scientific questions, we don't have huge changes at this point. But if there's a problem in interpretation, we'd like to hear it. Traceability matrices, and the rubric, and once again, take a screenshot of that link. I'll stop there. Thanks.
All right, thanks so much, Emily and Donna. The next up is the Landscapes and Seascapes Working Group, which has done an amazing job actually of making a pre-recorded version. So here it goes.
Hi, my name is Joanne Stock, and I would like to introduce you to the Land and Seascapes Working Group. The Land and Seascapes Working Group, or LNS for short, is broadly focused on geomorphology and active tectonics of subduction systems from the trench to the arc over a range of timescales. LNS is represented by a collection of scientists from the geomorphology, tectonics, structural geology, marine seismology, and volcanology communities whose collaborative efforts focus on imagining a broad, inclusive research program to further the study of geohazards acting across subduction zone land and seascapes. The community representatives on the working group are listed in this slide. In addition to this town hall activity, if you would like to contribute your ideas and interests to the LNS team, feel free to sign up for our interest group at SZ4D.org or follow us on Twitter at Surf and Turf. Also, please reach out as often as you like to people who are in the working group who you might know. We can make sure that your ideas and interests are heard in the working group to help us to be inclusive of the entire community as we build this exciting research program.
Hi, my name is Sean Gallen, and the LNS Working Group has worked together over the last year to develop a set of research questions and hypotheses oriented around understanding geohazards and subduction zones. Our overarching research questions are: how do events within Earth's atmosphere, hydrosphere, and solid Earth generate and transport sediment across subduction zone land and seascapes? And what fraction of a subduction zone's energy budget goes into building and shaping subduction zone land and seascapes?
Hello, I'm Brian Unitas, and I'm a member of the Landscape and Seascape Working Group. Our first question is, how do events within the Earth's atmosphere, hydrosphere, and solid Earth generate and transport sediment across subduction zone land and seascapes? This question has led to the development of a broad working hypothesis that sediment generation and transport is controlled by the frequency of drivers that initiate and mobilize sediment. When sediment is mobilized by storms more frequently than solid Earth events, for example, earthquake shaking and volcanic unrest, sediment generation and transport will be dominated by these large storms. Conversely, solid Earth events may play a large role in shaping landscapes when large storms are infrequent. Thus, the ratio of recurrence time of landscape impacting storms to landscape impacting solid Earth disturbances determines the role that atmospheric versus solid Earth processes play in shaping various parts of the subduction zone landscape. For example, when large storms occur frequently, landslide-related hill slip transport and hazards are dominated by these atmospheric events, whereas when they occur less frequently, earthquake shaking or intense volcanic rock weathering may play a significant role in generating landslides.
Hello, my name is Michelle Cook. For our second question, we seek to address what fraction of a subduction zone's energy budget goes into building and shaping subduction zone land and seascapes. The subduction zone system has energetic inputs and outputs. Energy is also transformed by a variety of both episodic and ongoing processes happening along the subduction interface, within the arc, and at the Earth's surface. The energy budget framework allows us to integrate these processes so that we can investigate their interplay. For example, we can posit that the style of upper plate deformation is regulated by convergence rate and angle, coupling along the subduction megathrust, elastic and inelastic deformation processes in the upper plate, body forces generated by topography, and the rheologic configuration of the upper plate. Some ways to explore this hypothesis would be to isolate the interplay between topographic loading and upper plate deformation and magmatism by comparing subduction zone segments with similar degrees of convergence rate, coupling, magmatic flux, and fore-arc lithotectonic complexity, but different mean arc slopes.
Hello, my name is Leif Carlstrom. Our working group developed a set of notional experiments to test the hypotheses derived from our key research questions. The design of our notional experiments follows the philosophy that tests of conceptual models require some sort of experimental manipulation in which relevant conditions are held constant while a single factor is systematically varied. In natural systems of the scale and complexity of entire subduction zones, this type of experimental manipulation is simply not possible. So our approach relies on comparing subduction zone segments where many of the relevant factors are known, such that cross-comparison may yield insights into physical controls on variations of a single factor. The paired experimental design may be used to falsify quantitative models of geomorphic transport, energy budget, and fore-arc deformation within subduction zones in a similar way as a strictly controlled experiment might. In the SZ4D framework, this approach is naturally integrative between working groups. Finally, such paired subduction zone segment design is useful for identifying the ideal geographies of our natural experiments, where controlled variations in the particular factors of interest may be present.
Hello, my name is Kristen Morell. We developed a science and applications traceability matrix that relates our driving science questions to needed observables, measurements, and new technologies. We use this matrix to identify and rank key measurement needs. For example, Tier 1 measurements denote those that cross-cut the vast majority of our research questions, while Tier 3 measurements represent essential observations that span a narrower subset of our key research questions. These Tier 3 measurements may be best facilitated by funding to individual PIs. Tier 1 priority measurements cross-cut almost all aspects of the land and seascapes question. These include, for example, comprehensive baseline high spatial resolution topography and bathymetry, and we'd like that to be less than 1 meter in spatial resolution. They also include repeat high resolution imaging in key areas where previous events might have occurred. And finally, continuous or campaign measurements of solid earth deformation from SAR and GNSS monitoring. Examples of Tier 2 measurements, which are designed to constrain rates of deformation, surface processes, and denudation on a range of timescales, include repeat satellite-based high-resolution optical images, ground-based environmental sensor networks, something like precipitation and stream flow, as well as temporarily broadband geochronology. So we're thinking radiocarbon, luminescence, cosmogenic nuclides, low temperature thermochronology. Examples of Tier 3 measurements include stable and clumped isotopes relevant to paleoclimate and elevation, as well as off and onshore sediment coring and paleoseismic trenching. These would be used to expand earthquake histories. In terms of infrastructural needs, these include robust cyber infrastructure for data organization, archiving, and distribution, integrated field-based experiments and observatories, and the development of support for high throughput geochronology facilities. Finally, numerical modeling is also regarded as a central tool for addressing the hypotheses arising from our key research questions.
Hi, my name is John Perkins, and I'll be discussing our working group's process to evaluate site characteristics and identify subduction zones that offer sufficient conditions to carry out the notional experiments. So we evaluated subduction zone segments in steps. First, we performed a comprehensive review of different subduction zone segments, which were defined for roughly equivalent along strike dimensions, about 200 to 400 kilometers, where tectonic, geologic, and climatic parameters were approximately constant. So then in the second step, the working group identified segments that would be problematic for study by the land and seascapes community, either because of lack of essential attributes or logistical factors that would prevent safe access to those areas. So then in a third step, we mapped our notional experiments onto sets of these subduction zone segments to determine those groupings that might be used to perform, quote, quasi-controlled experiments in which many properties were approximately equivalent, while a limited number of others varied. So this process helped us to identify a number of combinations of subduction zone segments that appeared to meet the design of the notional experiments, which will be used in the near future to identify geographies with common affinities, both to the faulting and earthquake and magmatic drivers of eruption working groups.
Hi, I'm Eric Kirby, and I'll give a quick overview of how we hope the SZ4D can engage communities of researchers in surface processes and active tectonics. With perhaps the notable exception of the critical zone observatories, these communities have not typically organized large, decadal scale, community-wide research efforts. Thus, the SZ4D project represents an unprecedented and an exciting opportunity to further the study of subduction zone land and seascapes through a coordinated community-wide program of research, outreach, and education. We see this degree of integration as central to the success of the land and seascapes component of the SZ4D, and we envision a network that includes researchers such as yourselves, institutions, and domestic and international partners collectively invested in the SZ4D. To grow and nurture this community, we propose a range of programs centered on land and seascape science that promote engagement, network building, exchange of ideas, and ultimately synthesis of results.
Hi, I'm Nathan Nemi, and I'll talk about leveraging existing community infrastructure to facilitate SZ4D research. The working group identified several strategies to build community, including SZ4D-sponsored graduate student and faculty exchanges with international hosting countries, a graduate student training network program, educational workshops, and coordination in scientific meetings. Also, SZ4D envisions an integrated program-level structure to organize, coordinate, and facilitate PI-driven research, as well as organizational and direct supportive facilities capable of handling SZ4D analytical needs, such as geochronological and geochemical data. Unlike many of the large centralized data facilities that can be used to process and archive remote sensing data, geochronologic facilities are numerous and heterogeneous in their instrumentation and protocols. We suggest drawing and expanding on existing NSF investments in EarthCube and EarthChem to ensure that analytical results are comparable across labs, methods, and subduction zone segments. Coordination between modelers, field scientists, and geochronologists will identify key modeling needs for coupled subduction system models. Organizations such as geochron.org, the Community Surface Dynamics and Modeling System, the Computational Infrastructure for Geodynamics, and the SZ4D Modeling Collaboratory were identified by the Landscapes and Seascapes Working Group as organizations with which partnering is needed to further modeling capabilities.
Hi, my name is Juliet Kreider, and I'm here to let you know the plan moving forward. We are beginning discussions about which subduction zones around the world could best serve as focus areas to study the sediment flux and energy balance questions that we have identified. In March, we will meet with the other working groups to identify cross-cutting themes that span the different disciplines of SZ4D, to discuss some pairings of subduction zone segments that will be fruitful for all the groups, and to construct a framework to integrate the science objectives of the three working groups. We will then identify those implementation structures that best facilitate a broad initiative and prepare an implementation proposal for funding agencies. We expect this process to accelerate throughout this year and to reach some conclusion in the fall and winter of next year. An essential part of this process is community input, both through town halls such as this, as well as through direct communication with your community representatives on the working groups. So please don't be shy. Reach out to any one of us to make sure that your voice is heard and your priorities are represented as we work to design an integrated and inclusive research effort that enables subduction zone science.
Okay, thank you. LNS Group definitely wins the Video Production Award for sure. The last presentation will be by the Modeling Collaboratory for Subduction Science by Ikuko Wada. And if we get the screen share off, then we can jump to the next.
Sorry, should I share my PowerPoint or?
Yes. May have to just, there we go. Now you should be ready to share.
Okay. All right, so
great.
Thank you, Harold. I'm Ikuko Wada from the University of Minnesota. So Modeling Collaboratory for Subduction has been mentioned by Harold as well as the working groups in their presentations. It is currently funded by NSF RCN, Research Coordination Network. And it is in the planning stage, just like SZ4D. This MCS is led by Thorsten Becker, who is the PI, and the steering committee members, including myself. Now, many of the members are not available, so I'm just filling in for Thorsten today. So our effort started in 2017 after or following the Boise workshop. And again, this visionary document produced by the workshop has been also mentioned, but in it, it indicates that a community modeling collaboratory is needed and is a key component of the SZ4D initiative. And more recently, the National Academy's consensus report also indicated that we need advanced computational capabilities and new methods of data integration. So the objectives of MCS, at least one of them, is to provide a modeling framework for multidisciplinary data integration, which is important as we are getting data from various observations. So it's highly multidisciplinary. And to understand the processes we are studying, we really want to utilize them and incorporate them. And how do we do that? And MCS will try to address that. Another objective is to increase or promote and facilitate open and reproducible collaboration and research. And this is also important if we really want to integrate multidisciplinary data. And another important thing is that computational geoscience can make geoscience more accessible to some populations who are not really physically able to participate or experience science. And with this, we can increase, with computational geoscience, we can increase inclusivity and also STEM capacity. So that's another goal of MCS. So again, the processes that we are trying to understand are generally multi-scale, so occurring at a range of time and length scales. Many of them are strongly coupled. And so integrating these processes is a challenge. And again, that's one of the things that MCS is aiming to address. Assimilating multidisciplinary and heterogeneous data is another one. Clearly, we want to quantify unknowns, but MCS aims to also quantify uncertainties as well. And that should help design future experiments to minimize these uncertainties. So what MCS should look like or should provide to the community has been discussed largely through workshops and webinars. We have been organizing 3 workshops. The first one focused on fluid transport, as fluids are really important components to many processes, including earthquakes and volcano systems. And so one of the things that came out of the workshop is that MCS can provide a modeler modeling framework to link different components, and could be different groups studying different parts of the subduction system. But this needs to be done in a consistent manner to get meaningful results. There are other specific things that people thought MCS should provide, such as resources for effective communication, benchmarking exercises, regular workshops for community building, and also support for PI and community to access computing technologies. So MCS is really not just for providing modeling framework, but for community building as well, and also bridging different communities, for example, earthquake and volcano communities. And in SZ4D context, it could be bridging different working groups. The second workshop focused on megathrust systems. And again, they focused on or emphasized on the role of MCS on international and open collaboration. And there are other specific things that are discussed. And these are all summarized in our workshop reports. So I will refer you to those reports for details. The last workshop that is currently ongoing, as Harold mentioned, is on volcanic system modeling. It's in the form of a series of webinars and also working group meetings, and this is going on until May. And once we have a report from this workshop, we will be combining or synthesizing all three reports to come up with a set of recommendations. Now, if MCS is probably going to be a small fraction of what SZ4D is going to be, but if we can incorporate MCS's recommendations in an effective way, in coherent and consistent way, I think we can make the SZ4D recommendations even stronger. So now we don't have any breakout on MCS related topics, but I heard that there's going to be a breakout on rock and modeling for the faulting and earthquake breakout room. So we are hoping that we can also collect some input on MCS related things. And there's another steering committee member, Alice Gabriel, is going to be definitely in that breakout. Thank you.
Okay, thank you so much, Ikuko. Well, everyone, we've thrown a lot at you, but we are going to have these breakout groups now for open discussion, and I'm going to share a slide again and then turn it right over to Emily to organize the breakouts.
Okay, so breakout time. First of all, we have run over in our presentation time, and so we have decided that we are not going to do a plenary report back of the breakouts, that it was more important to preserve maximum breakout discussion. You will capture your breakout discussions in Google Docs, and then those docs will be the report back rather than trying to do it all verbally in an hour. So what we're going to do now is there are 7 breakout rooms. And you should pick your interests. If it's building equity capacity, magmatic drivers, landscape, seascapes, or faulting and earthquakes. For the first 3 of those, simply for building and equity, there will be 1 breakout room. For magma drivers and eruptions, there are probably enough people. We should have 2 breakout rooms. And so we're going to do that based on your birthday. Based on what we have a good random sampling. If your birthday is before June, go to A. If your birthday's after July and on, go to B. Same for landscape, seascapes. Faulting and earthquakes, we're going to do it a little bit differently. We're going to do the first breakout room will be instrumentation, and the second one will be rocks and models, meaning geology experiments and modeling. You should be able to self-assign yourself to a breakout room. And so if you can, your Zoom lets you do it, just go. They're open, right, Natalie? They're open. You can go. If you cannot get yourself there, you're trying to get yourself there and your Zoom is not letting you do it, rename yourself to your desired breakout group and Natalie will move you there. Natalie is the administrator who works with us here at SZ4D, and she will move you there. So if you just say, change your name to Magma Drivers B, she will move you there. Try the self-service model, and if the self-service model fails you, she'll help you out. See you there. Off you go. I'm going to finish my thing that was just being said to FEC because I think it's for everybody. The docs are alive forever, but comments on them would be most useful within the next couple of weeks.
And I think we'll all be following up with ways to give us various mechanisms to give us feedback. But those docs, email us. We have various surveys by whatever means.
The sooner you give comments, the more quickly we can incorporate your information.
Yeah, let me broaden that to say a couple of things. One is that we've recorded the presentation portion of the Zoom. The breakouts are not recorded. We're going to turn those around and try to post those to the SZ4D.org website as quickly as we can, hopefully by the end of the day. We're also going to have on the website a link to a little Google survey form as a way to continue to provide feedback and input. In each of your breakout rooms, the leaders were capturing notes, hopefully. We wanted to keep this thing brief enough, so we're not going to take the time to do a report back here on the spot. But all of that information is flowing back into each of the working and integrative groups. All that information is flowing back to the steering committee. And the whole point of this exercise is really for us to make sure that that you're learning what's happening inside those various groups that are working hard on these things, and that your feedback is getting back to them in really meaningful ways. So go to the website, SZ4D.org, to look for that information. It'll take us a little bit of time to post the video, but we'll get it up as soon as we can. And then the survey link will be there as well. It's open for people to put any kind of feedback they want to any of the groups, really at any time. But in particular, right following this town hall. Next thing I want to say is that this isn't going to be the last town hall by a long shot. We plan to have a number of these over the course of 2021 as we just go through step by step. People don't have to attend every one of them to feel like they're not missing out, but there will be plenty of opportunities, we hope, for these kinds of forums. We also are in the stage of planning for some topical town hall style or smaller meetings that will just be opportunities for input directly on specific subtopics sort of within the overall SZ4D effort and initiative. This thing is grassroots and ground up as much as we can possibly make it. There's a huge research community, obviously, around the whole world, as well as inside the US, to do these kinds of activities. And we are trying as hard as we can to be as representative as we can of that entire community. Prioritization has to happen, but input is absolutely essential. I'd love to just offer a moment for any of the other speakers or working group leaders to say any final thoughts. We do want to close this thing out in just a few short minutes. Okay.
I think we just need to say thank you to everyone for, it's such a busy time, and thanks to all of you for taking the time to engage with us in this. We need all of you to make this be the program that we want it to be. So thank you.
And boy, do we look forward to seeing you all in person at a town hall at some conference coming up in the future. That is going to be when all of this hard work starts paying off and we get together and actually talk about it. That will be an exciting time. All right, well, we're right on the dot. So with that, thank you everyone for participating today. Again, stay engaged and check our website regularly for updates and for upcoming webinars and so on, and sign up for our mailing lists if you haven't done so already. With that, thanks to all. We'll close it out.